Okay, Sergi Blanco-Cuaresma is going to talk about deep learning with all of the entire publications of astronomy for the last 200 years. It will be interesting to see what we can learn. Sergio works at the ADS in Cambridge, although he's probably not there right now. So you can take it away, Sergi.
Thank you, Jessica. So as many as you know, ADS is a database of scientific articles, especially focused on astronomy and astrophysics. And right now it contains more than 14 million entries and more than 129 million citations. And the core of ADS is a search engine that is named Apache Solar. This search engine is specialized on textual data, which means that, for instance, it's going to take titles, abstracts, full text of articles, and it's going to go through the sentences and just focus on the individual words of those sentences. And then we could have like sentences like the one that we have in the screen, and it's going to, in the first pass, discard those words that we call the stop words, or those words that are less meaningful for doing searches. And then it's going to count the number of words that appear, the number of times that those words appear in each document in the whole corpus, and also the number of times that the word appear in each individual document. So that by combining these two frequencies, whenever a user searches something in ADS, the results are going to be sorted with some scoring that is based on those frequencies. One of the difficulties of this approach is that sometimes, in the natural language, there are words that have very similar meaning. Like it could be a corner store or fundamental in this example, or sometimes you have exactly the same meaning, but you just have a different spelling between British English and American English. Right now in ADS, what we do to overcome this kind of limitation is that we maintain a quite large list of synonyms where, when somebody searches something like gravity or gravitational, both things are going to end up searching both words. So a way of trying to improve this and trying to make our lives also a bit easier, maintaining this large list of synonyms, would be like, what if we take all these words and we actually convert them to vectors, so that we have a multidimensional space where we can locate all these words with different points in the different dimensions. But what if even we go farther away and instead of just having all these words converted into random positions in that space, what if we manage to group, to distribute them in a way that those words that are more similar, they end up closer together in the space? So we would be transforming these words into vectors and finally what we call semantic vectors. So that's exactly what we've done using a package library that is called Chai, and we've trained we've actually built and trained a neural network with using more than 800,000 abstracts from ADS, so that now with the help of this package, we can do something different. So we can still start with what we had before, so the frequencies of the words and so on, but now we can look at the corresponding vectors of each of these words, and we can search around the position of those vectors and identify, oh, okay, so when a user searches something, there are other words that are similar to this word that the user has searched. So we can search not only for the exact match that the user has written out. And just to provide an example, a more illustrative example, let's imagine that a user searches tidal effects on exoplanets. When we introduce this query using Chai, one of the first articles that appear is this one. And the interesting thing here is that whenever you check the title or or the abstract, it's only the word tides that appears, not the word tidal. And we have not, for this experiment, we have not used any list of synonyms. So really the system has learned that these two words have a very close meaning, and it's capable of identifying then documents that are relevant to this search. The same actually happens also for effects, where it appears in the abstract, but only in singular, not in plural. So this is great. So we have all these semantic vectors, but we could even go one step farther, and we could say, what if instead of just focusing on these individual words, what if we actually take the full abstract and we convert that abstract into also semantic vector, so that it captures the semantics of the abstract and in the end the topic of the paper. So we could then have this same multidimensional space, but now instead of individual words, we would have these abstracts distributed. That's what we've done using something called sentence transformers, specifically as SVERT. I will not go into the details. Basically, this is using the language model from Google named Google BERT, and we've again created a selection of 800,000 abstracts for which we have computed all these semantic vectors, so that we have all these abstracts in this multidimensional space. One thing interesting, having once computed this whole corpus, is that whenever we have now a new abstract that appears, we can easily take that abstract, convert it into the proper semantic vector, and then we can use approximate nearest neighbors algorithms that are, for instance, implemented in the Facebook library named Face, or in the Spotify library named Annoy. We try both of them, and both work pretty well. By having this vector and using these algorithms, we can very easily and very fast scan a large amount of data and identify what other papers are nearby. So this is going to allow ADS to do a faster and better classification of new articles. Another thing that we can do once we have this data is, of course, apply clustering algorithms, like for instance the typical k-mean algorithm, which would allow us to detect a group of papers that talk about the same topic in an automatic way, just focusing on the content on the semantic content of these papers. So all this is pretty nice, and we've been using all this content, and we've been basing all these experiments on the semantics. But actually, ADS has more than that, because in ADS we also have known relationships, as you all know. We know that there are papers that cite other papers, and we have all these relationships already detected in our database. So we thought, okay, then it would be interesting if we can take these known relationships and we can import them into a graph database. Specifically, we are trying Neo4j, and here we imported this data with all these relationships plus other relations, like for instance, this author created this paper, or this paper are about these keywords, and so on. And Neo4j has been shown to be really fast when we do queries, and also the language that is used to do queries on this database, it's a very expressive one. It's a language that is called Cypher. And just to give you an example here, this is an example of a query where everything that is in parentheses, it's like I'm asking for a node. So if we read the query here, we have, I want to match the abstract that is identified with the bibcode X, and I want to also identify all the abstracts that this paper cites, and finally I want to identify all the authors that created those papers. So as you can see, with just that single line, very expressive language and easy to parse, we get back all these results that we see on the screen. And when we compare these to things like SQL, you can see that it's clearly more, it's easier to understand and to build a query in Neo4j than in SQL, where you would have to do one or multiple joins to retrieve the same kind of information. So something interesting, once you have all the data in Neo4j, is that you can apply algorithms that Neo4j provides for the data analysis. Like, for instance, we can very easily use or apply the PageRank algorithm. This is an algorithm that is going to detect nodes, or in this case, abstracts in our network that have a higher importance. And by this, I mean, like, for instance, you know that if you go to ADS and you search for something, you can just sort your results by number of citations. With PageRank, we would not just stop at the first level of citations. Like, for instance, if we check the document on the bottom, we see that this document has one citation coming from a paper that has also one citation. But if we compare to the document next to it, we see that same situation, it's a paper with one citation, but it has the paper that is citing has two citations. So in this scenario, PageRank would provide a higher rank, higher weight to this second document. It would consider this more important. As to make an example, or to show an example, this is a query with showing papers from a given author, and we are showing here the computed PageRank and the number of citations. And as you can see, they don't have to correlate. In this case, this author has a paper with some first level citations, but the impact that it has had and the importance that this paper has in this network is higher. So this is an interesting way of exploring the data. Also, something that we can do with Neo4j is apply community detection algorithms like the Louvain algorithm. In this case, again, what we are doing is just by looking at the relationships, the system or the algorithm is able to detect, oh, okay, so we have here like a cluster of papers that strongly cite each other. So, and most probably these papers are related somehow. So we can see some general patterns where papers that talk about stars or papers about cosmology, they tend to be clustered and detected by this algorithm. They are detected together. So I should end up saying that everything that I've shown here, these are really results from things that are not in production right now. These are really preliminary exploration that we are doing in ADS for future future features. So as a summary, we've seen that this can be a very interesting way to use semantic representations to improve or augment the synonym list that we are using internally in ADS. We've seen that this strategy could also help developing features where we could score documents and articles based on the importance that they have in the graph. And finally, we've seen that this kind of technology can allow us to very fast classify new documents, or even cluster documents that we already have in the system based on the semantic content of them, but also we can rely on the known relationships, so we can combine these two methodologies of clustering and detecting community. So this is all. Thank you very much for your attention. I'll be happy to answer questions.
First question I'm reading off of the Q&As is how you translate a word into a vector, and what are the components?
That's a very good question. So there are already algorithms that exist, like word2vect or fasttext, that do this kind of thing. What it happens behind the scene is that you train a neural network where one strategy is, for instance, you have a sentence and you just take one word in that sentence, and that word you just convert it to a vector. That first vector is going to be completely random. It's random, but it's within a vocabulary, so that you can always associate your words to concrete vectors, and then that's going to be the input of your neural network. And then you train your neural network so that it's going to predict the words that are around that input word that you've provided. And by doing this kind of training, you can end up using just the hidden layers of that neural network as a semantic representation of your original word.
Okay, then I'll combine two questions and that'll be it, I think. One is, when do you think it will be put into production or in a beta testing mode? And the second question is an interesting one about how does it work with abstracts in languages other than English?
So we have, for the second part, we have not explored yet language models based on other languages, but that's a very good idea and something that we totally should do. And regarding the first question, when it's going to be put in production, so this actually is going to highly depend on how good we do in hiring a new machine learning engineer. As I'm saying here, we are trying to hire, we have a new open position. So it's going to depend how successful we are finding a good candidate, and so that we can give a big push to this kind of project. So that's, I hope it's going to be soon.
We'll close off now and move on to the next speaker. So thank you very much, Sergi.
Thank you.